All right, let's go ahead and get started. I do want to welcome you to this final installment of Unit 2. This is Atomic Theory. We're going to be taking a look at a couple of challenge questions here just to make sure that we understand the material well and that we are prepared for the examination. So here we go. Number 1 says, explain J.J. Thomson's cathode ray experiment and explain what it revealed about the nature of the atom. So remember that before J.J. Thomson, that Dalton and even before him Democritus had stated that the atom was the fundamental unit of nature, that there was nothing smaller than the atom. In fact, Dalton had used his experiments involving the law of definite proportion and the laws of multiple proportion to establish this fact that there was nothing smaller than the atom. But then comes J.J. Thomson, and he uses this special tube called a cathode ray tube, and he essentially does this. He shoots a cathode ray through the tube, and this I'll use to denote the cathode ray. But as he passes the ray through some plates, a positively charged plate on the top and a negatively charged plate on the bottom, something very interesting happens, and that is that the ray is deviated, right? And in fact, it's always deviated toward the positive plate. So after a number of calculations, J.J. Thomson surmised two things. First of all, that this cathode ray was not light at all. It was not like a light from a bulb or a candle, but in fact it was a stream of particles. So you could think of this cathode ray then as being a stream of these small particles. Now, after calculations, he determined that the particles were very small. In fact, something astounding came from those calculations, and that is he deduced that the particles were, first of all, negatively charged, but that they were very, very much smaller than the atom itself. He called these particles electrons, right? He called them electrons. Now, this completely shattered the idea of Dalton that the atom was the fundamental unit of nature and that there was nothing smaller, because now J.J. Thomson's experiments revealed that the electron was the smallest particle in nature. So that meant that the whole model of the atom had to be revised. Rather than being a single sphere, J.J. Thomson envisioned a sphere with these little particles called electrons embedded throughout the atom like plums in a plum pudding. So he calls this model the plum pudding model of the atom. Okay? So that's J.J. Thomson's contribution. Now let's take a look at Rutherford's contribution. Rutherford's gold foil experiment refined our ideas of the atom. Explain this experiment and how it changed our concept of the atom. Well, J.J. Thomson had told the world that the atom was composed of these small particles, that these small particles made up the atom, and that they were throughout the atom like plums in a plum pudding. So that meant this. That meant that if you were to take a piece of gold foil, or at least this is in the mind of Rutherford, if you were to take a piece of gold foil, and that gold foil was composed of these atoms of gold, and that those atoms contained very, very small particles, right, called electrons, that you should be able to fire a particle, a large particle, like, say, for example, an alpha particle, and that's exactly what he did. He fires an alpha particle into the gold foil. That gold foil, that alpha particle should go straight through the gold foil. So if you shot repeated alpha particles through the gold foil, there's certainly the little electrons were not big enough to deviate the trajectory of the alpha particle. And so most of the alpha particles hit right in a straight line from where they were fired. But every once in a while, the particles, the alpha particles, would deviate off course. They would go to one side or the other. Sometimes they would even come right back from where they were being fired. Well, that was intriguing, because what that meant was this. What that meant was that the atom was not simply composed of electrons throughout, but rather it must have a dense core, right? And it was deduced by Rutherford that there was a positive core, and he calls this core the nucleus. So now, once again, our model of the atom is modified. A dense, positively charged core with electrons strewn throughout, right? So we leave now the plum pudding model behind, and it was later discovered that the positive core, this what we call a nucleus, contained protons and neutrons, right? Protons and neutrons. So this now is our new model of the atom as proposed by Rutherford. Now, the next question has to do with Niels Bohr's contribution to modern atomic theory. And in fact, Niels Bohr's model is very much like the model that we learned about in grade school, with the nucleus in the center of the atom containing the protons and the neutrons and the electrons circling throughout in special orbits like planets around the sun. So that is our modern conception, or what we believe, at least to this point in our education, we believe that the atom is. Again, protons and neutrons in the nucleus, electrons circling around like planets around the sun. Okay. So that model of the atom has served us well, and we'll continue to use certain aspects of that model. But it's really Irwin Shroedinger's modern atomic theory that we believe to be the most reliable in terms of what the model of the atom actually is. It's a very, very complicated model. It is based on probability. And in fact, what Schrodinger says that it is not possible to tell exactly where the atom is, or the electron, I should say, is at any given time. The electron can only, you can only determine where it's most probably going to be. In other words, there might be a space very near the nucleus where the electron is most likely to be. But there's another space, say here, where the atom is, the electron, I should say, I'm sorry, is not likely to be. And then there's another high density area and so forth, right? So the ideas that Schrodinger places forth are very complex, and we're going to learn more about those actually in our next unit. But that's it. That's all we need to know for now about Schrodinger's contribution to modern atomic theory. Number 6 asks about the difference between ions and isotopes. Okay, so let's start with ions. What do we mean by an ion? Well, I've made a little table for us here. If I have an atom that has 6 protons, and by the way, it might be helpful for you to have a periodic table in front of you right now. But if you have 6 protons in the nucleus, right? If there are 6 protons in the nucleus, then protons define the atom. Not the number of neutrons, not the number of electrons, but the number of protons. If the atom has, say, 5 protons in the nucleus, it's not carbon, it's something else. If it's neutron, if it has 7, it's nitrogen, right? But if it has 6 protons in its nucleus, it's carbon. Now, the number of neutrons may vary, but if the number of protons and the number of neutrons, the number of protons and the number of electrons in the periphery are not the same, then you have an ion. Now, notice protons are positively charged, electrons are negatively charged, right? So in this case, I've got 6 protons, I've got 6 electrons. This is not an ion. This is simply a carbon atom, okay? That's it. It's just a carbon atom. Now let's look at the next one, however. This time we've got 9 protons in the nucleus. Remember, we're looking at the relationship between protons and electrons. We've got 10 electrons in the periphery. So remember that the 9 protons defines the element. If I look at my periodic table, I see that this is fluorine, right? So this is fluorine, but it's not just a fluorine atom because there's one more electron than there is protons. Because there's one more electron than there are protons, we call this a fluorine ion, right? And it has a negative charge. And we'll write it like this, F minus 1, just like that. Negatively charged atoms are called anions. Anions. Positively charged ions are called cations. So cations are positive, anions are negative. All right. Also, if you look at your periodic table, and I realize we haven't gone through that unit yet, but you should know a few things about periodic tables just from middle school and elementary school, and that is this. If you look at the left side of the periodic table, elements on the left side of the periodic table like lithium, sodium, potassium, beryllium, magnesium, calcium, those tend to form positively charged cations. Elements on the right-hand side, fluorine, chlorine, bromine, oxygen, sulfur, selenium, those tend to form negatively charged anions, okay? So positively charged cations from the left, negatively charged anions from the right, okay? So that'll do it for ions. Now let's talk a little bit about isotopes. Well, as it turns out, isotopes have differing numbers of neutrons. Now, I'm using what's called a nuclear symbol for these two isotopes. Now, carbon, of course, is the symbol from the periodic table, or C is the symbol from the periodic table for carbon. But look at the number here on the bottom. This number on the bottom signifies the number of protons. So if you have 6 protons, it's going to be carbon. That's for this isotope and this isotope. But look at the numbers on top. What are those? Those are called the mass numbers. And the mass number is the number of protons plus neutrons. Protons plus neutrons, just like that. So let's take a look at this isotope on the left. I've got 6 protons and I've got 6 protons and I've got 12 protons and neutrons. So if there's 6 protons and 12 protons and neutrons, how many neutrons do I have? That's right, 6 neutrons in this particular isotope. But now let's look at this one. I've got 6 protons and 14 protons and neutrons. So what's the difference between 6 and 14? 8. So I must have 8. There must be 8 neutrons in this particular isotope. So these are 2 isotopes of carbon. One we'll call carbon 12. We can abbreviate that as C12. And the other one, carbon 14, we can abbreviate that one as C14, just like that. Okay? All right, here we go with the last question. Number 6 says the average atomic mass of an imaginary element is 54.38 AMU. One of its 2 isotopes has a mass of 52.52 AMU and a relative abundance of 84.23%. What is the mass of the other isotope? So I've made a little table here. So here I've got the mass of the isotope that they're talking to me about, the 54.52 AMU for one of the 2 isotopes, and we're looking for the other mass, right? Now, I'm told that the 52.52 AMU isotope has a percent abundance of 84.23 that I'm going to convert to decimal form 0.8423. Now, where did I get this 0.1577? It's not in the problem. Well, here's what I know. That if there's only 2 isotopes, right? If there's only 2 isotopes, then, and it tells me here that there's 2 isotopes, then these 2 numbers, 0.8423 and 0.1577, have to add up to 100%, or in decimal form 1. So to get the 0.1577, I simply said 1.00 minus 0.8423, okay? And so what we've got then is the information that we need to solve this problem. Because remember, if I multiply the mass times the percentage for each isotope, then I'm going to get the average. Well, they tell me that the average, now this is a weighted average, but it's an average nonetheless. The average atomic mass of the imaginary element is 54.38, right? So 52.52 times 0.8423 plus, this is what I'm looking for. I'm looking for the mass of the other isotope. So I'll call it X, times 0.1577, and that's equal to 54.38. I'm going to solve for X now. I'm going to consolidate on the left-hand side. I get 0.1577. X is equal to, I'll bring this, or 54.38 is already on the right-hand side. 52.52 times 0.8423. I'll bring that 44.24 to the other side. So I'll have to remember to subtract it. Then I get 0.1577x is equal to 10.14. X then is equal to 64.30.